Hi everyone. So I had a back injury, so I'm recovering from that. And so since I had some time, so I thought I'll discuss a very interesting circuit, um, which this was a question that was posed to me by a student of Professor K. Radhakrishnan Rao. So Professor K. Radhakrishnan Rao is the analog guru from IIT Madras. So he used to teach in 1980s and 1990s. So he had created a generation of analog engineers were in very good positions across the world. And he also happens to be the teachers of all the best analog talent in the who are all in very senior professor and managerial positions in different analog companies in India and across the world. So I had the fortune to discuss with Professor K. Radhakrishna Rao not about the circuit, but about his experiences at IIT Madras when I was interning at Texas Instruments. So he used to wait for his cab in the evenings. So he used to have some time. So I used to discuss with him about his life at IIT Madras. So this question was posed to me by one of his students in my interviews, and I had answered it back then, and I thought I'll discuss it now. So we'll look at it. We'll not go very deep into the mathematics of this problem, or we will not do a very deep nonlinear analysis. Intuitively, we'll try to guess what is the output of the circuit and what's actually happening in the circuit. So the question that was posed to me had multiple parts, so I'll discuss all of that. Okay, and see, it helps us gain a good understanding of feedback and all of that. The circuit shown here is a logarithmic amplifier. So logarithmic amplifiers were popularly used in the first generation analog amplifier circuits. So they were used for voltage multiplication, they were used for voltage division. Again, as I said, uh, op amps can be used to realize a range of nonlinear functions. So this is one such circuit. Okay, so we'll see its operation in a few moments. The question that was asked to me was a square wave input, which goes from 250 millivolts to 1 volt, was fed as an input to the circuit. Okay, and in this circuit, the op amp is not ideal. It has a very high gain, and the second pole is almost a decade away from the UGB. So it's almost like a dominant pole, a single pole system, and the phase margin is close to 90 degrees. The question was, how do you think approximately, you can use some linear approximations and all of that, and tell what will be the step response to the circuit. So this is a logarithmic amplifier. So therefore, if your feed, so the input is changing from 250 to 1 volt. So it's like a 4x change. But since it's a log operation, it's going to be smaller. A logarithmic function is like a compressive function. So it's going to be a smaller change at the output, right? So even though there is a huge change, even though if you have an exponential change at the input, you take log of that, you will see a linear change at the output. Okay, or if the input is changing by linearly, the output is going to change in a much smaller and graceful way. So rather it's a compressive change. Okay, so logarithmic function, if you look at the log graph, it's going to look like this for 1 to infinity. So as your input increases, even though the input changes significantly, after a point the variation in the output is going to be much smaller. So a logarithmic function is also called a compressive function for that reason. The question here is that how will the response look like at the output uh, given the loop gain, given the op amp's open loop gain response, which looks like this. The phase margin is 90 degrees, which means it's almost like a single pole system. The second pole is almost a decade away from the UGB. So first we'll analyze it assuming that the loop gain, the op amp is ideal, and see what should be the output. And then we'll predict the output assuming the op amp is non-ideal. So assuming the op amp is ideal, I just said it's a logarithmic amplifier. So VI by R, assume this is a negatively feedback circuit. So you increase your input here. So this circuit will generate a current and this node will increase. So this is like a common base amplifier. You increase the emitter, the collector voltage will also increase, and that will decrease the output, right? So it's a negatively feedback circuit. And so because an increase at the output is met by an opposing change, so therefore we said such circuits, whenever you traverse the loop, you will have a total 180-degree phase shift, and such circuits are what we said negatively feedback circuits. Now, since it's negatively feedback circuit, we said we can assume that the error is 0, it's an ideal op-amp. So this node becomes a virtual node. So the input current Vi by R is the same current that's going to flow through this BJT here, and that current is going to go into this op-amp. Okay, so the output voltage, I mean the input current, the current through this BJT is set by two conditions. Of course, one is Vi by R, that will exactly be equal to the collector current, which will be equal to IS, the reverse saturation current of the BJT, times e power Vi by Vt. Okay, Vt is the thermal voltage. Approximately its value is 25 millivolts at 300 Kelvin. So the circuit, I forgot to mention in the beginning, we have to analyze the circuit at 300 Kelvin. So you can just do some very simple manipulations. What you will get is that the output voltage V0 will be minus Vt times ln of Vi by Is into R. Okay, so this is the output. And now we will just analyze what happens when I feed a step input. So I'm going to feed a 250 millivolts input first. So this is like 10 times Vt. If Vt is 25 millivolts, 250 millivolts is almost like 10 times Vt. That's the input I'm feeding. So if I feed 250 millivolts, so let's call that voltage as minus of Vt ln of Vi upon Is into R. So Vi corresponds to 250 millivolts. So you will get some negative voltage whose value is given by this. Okay. Now, when you apply 1 volt, so that's like the input becomes 4x. Now, instead of Vi, it's going to be 4 times Vi because 250 times 4 is 1 volt. So the input that you're applying right now, I can simply write it as minus Vt ln of 4 times Vi by ISR. So if I take the 4 separately outside, so you would get something like this. So you'd get an expression which is minus Vt ln Vi by ISR, which is the input corresponding to 250 millivolts, minus Vt ln 4. Okay, so Vt ln 4 minus Vt ln 4, this term comes to around minus 35 millivolts. So even though input is changing by 4 times, which is 750 millivolts, is changing by a factor of 4, the change in the output is going to be much smaller. So that's a logarithmic compressive nature of a logarithmic function. So the change is much smaller. It's only minus 35 millivolts. So what you should expect is a negative value whose value is minus Vt ln of 4 Vi by ISR. So Is is not given and R is also not given. So we can just assume that it's negative value. And when you apply a positive step of 1 volt, the change in the output is going to be a negative step whose value will be minus Vt ln 4, lower than the previous value, okay, which is minus Vt ln of 4 Vi by ISR. So this is what I should ideally expect if this op-amp were an ideal op-amp. But this op-amp has a finite loop gain. Okay, sorry, so this is not a right representation. So here we just discussed the phase margin is 90 degrees and the second pole comes much farther away from the unity gain bandwidth. So unity gain frequency is omega u, second pole was almost at 10 times omega u. How will the responses look now? So before we analyze circuit, what is important to us, what dictates the step response of a system is the loop gain. That's the most important parameter. It's not the open loop gain of the op-amp, but the loop gain, okay, of this circuit, which is going to dictate the closed loop response of the circuit. So to analyze the loop gain, I've always said pick a point where the impedance looking in is infinity. So I can pick this point. So the loop gain can simply be written as A of S times. So if I apply a voltage, say delta V here, you will get minus of A of S times delta V here. And this is a common base amplifier. So that whatever change you have delta V here, you will generate a current whose value will be Gm times delta V approximately. And that times R will be your loop gain. So loop gain will simply be, so it's just a common base amplifier. Collector is connected to a resistance of value R. So the gain will simply be Gm times R. So you'll have A of S into Gm times R. Of course, the loop gain is negative because it's a negative feedback circuit. So this is the loop gain expression. Now, if you see here this loop gain, conventionally, when we analyze linear op-amp circuits, typically the loop gain will never exceed the open loop gain, right? Beta, the factor beta will always be less than 1 or equal to 1. But in this circuit, the factor beta, so this is, you can assume that the signal quantity from output voltage to the input of the op-amp. So I'm going to call that as beta. So that is greater, it is equal to Gm times R. Okay, so we'll see what is the value of Gm times R in the circuit. So first, Gm in the circuit is simply given by the collector current times divided by Vt. So this is the expression for Gm of a BJT, linearized Gm. Now times R, so IC into R by Vt. Now what is IC? The collector current is simply Vi by R. Okay, so that's the collector current. So I can write it as Vi by R. So R and R cancels out. I get Gm into R or beta simply equal to Vi by Vt. Now here is a circuit whose feedback factor beta is a function of the input voltage. So it's a nonlinear circuit. So you should expect such such behaviors where the loop gain also is a function of the input voltage. So for the case when the input voltage Vi is 250 millivolts, your beta is 10, right? So it's Vi by Vt. So since I said Vt is 25 millivolts to 300 Kelvin, Vi is 250, which is 10 times Vt, so beta is a factor of 10. Now you should multiply this with the loop gain. So what would happen is that the whole graph would shift. So previously the loop gain was something like this. So you had the first pole and the second pole was coming much later after the UGB. Okay, but now the whole graph is shifted by 10 or 20 decibels. So it increases by 20 decibels, okay, by a factor of 10. Now, since your second pole was almost a decade away, now the second pole will come much closer to the unity gain bandwidth because unity gain frequency itself increases. Therefore, your phase margin is now going to convert. So again, I've made a lot of approximations here. The phase margin is going to be slightly less when you do an exact analysis. But I've made an approximation. What happens when your UGB is approximately equal to the second pole? So the first pole has already created a phase shift of 90 degrees. The second pole will create a phase shift of 45 degrees. So the total phase shift is going to be 135 degrees. So the phase margin is going to be 45 degrees. So now your phase margin has decreased. So the moment your phase margin is 45 degrees, so if you recall from basic analysis, the loop gain, closed loop gain is going to look like this. The closed loop gain plot will have a peaking, and the peaking is approximately 1.3 times the DC value. Okay, this is the closed loop response. So you should expect some kind of a ringing behavior in the frequency domain, in the time domain. Okay, because previously phase margin 90 degrees, it's going to behave like a first order system. But now the phase margin is 45 degrees. So therefore, you should expect some kind of a ringing behavior. In the second case, where your input goes to 1 volt, almost 4 times, your beta is going to be 40. Your beta here is Vi by Vt. So Vi is now 1 volt by 25 millivolts, so it's going to be 40. So it's going to further increase, your UGB is going to further increase, and it's going to come much later than the second pole. Okay, so you can easily, in fact, I've written less than 40 degrees, your phase margin will be less than 20 degrees or so. It will be much lower. So generally, the rule of thumb we use is 45 degrees per decade. So, it's not a decade yet. So we should expect a significant degradation in the phase margin. So right now I'm not worried about the exact value. So you should know that because previously the gain plot was something like this. So your UGB was much smaller, but now the UGB has increased almost 40 times. It's not exactly 40. It depends because second pole also comes into the picture now. So it has increased by a large value. So you should expect a significant degradation in the phase margin. Okay. So what we should know is that when your input signal changes to 1 volt, the phase margin degrades even further. So now keeping these 2 points in mind, we'll try to roughly draw the output waveform. So initially it is 250 millivolts. I'm applying a step of 1 volt. The moment you go to 1 volt, the transconductance increases by a factor of 10, 40. It goes to 4 times its value of 250. The phase margin is very poor, so you will see a large ringing response, which is what I've shown here. So even though it's like a step input, For an ideal op amp, you would expect a smaller step change, but here it's going to be a large ringing response. And this, of course, the total change will be minus Vt log 4. On the negative step, when your input is going from 1 volt to 250 millivolts, now here your GM is decreased. Therefore, your loop gain decreases. So loop gain is still 10 times higher than its open loop gain, but its value is 10 times A0. So if A0 is the open loop DC gain of the op amp, for 250 millivolts input, the DC gain is going to be 10 times A0. For 1 volt input, the DC gain in this region is going to be, DC loop gain is going to be 40 times A0. So it's significantly ringing because your UGB has moved farther away the second pole. In this case, it's 45 degrees. So you will see some peaking and it's going to ripple. It's going to have some ringing and settling. So, but of course, the negative step will have a much larger ringing because the phase margin is going to be much poorer. I've written 40 here. In fact, it will be even less than 40. Okay. I'm sorry, I didn't get time to look at the exact values, but you can, I mean, as I said, you just want to get the intuition behind it. So it's going to be a smaller value. So it's going to ring significantly. Now the question is, which they asked me was that, of course, I answered this part, but what they asked was, can you make this response symmetric and stable? Because if you see, there is asymmetry here. So for a negative step, you're having larger ringing. For a positive step, you're having a larger ringing. Sorry, this is a positive step. You're having a larger ringing at the output. And for a negative step, you're having a smaller ringing. So can you first make it symmetric? And second, can you eliminate ringing? Can you make it more stable? Okay, so since your phase margin is very small here, it can, it's less than 20 degrees. There are chances that the loop can even go into an oscillation condition. So the question was, can you stabilize this? Now remember, you don't have access to op amp. So this is a discrete op amp circuit. So you don't have access to, let's assume that you don't have access to compensate this op amp. Okay, so then we have to do something to this external circuit such that it stabilizes this circuit. Okay, so when I'll probably upload some videos on CMOS op amp design where we will talk in greater detail about compensation, but right now I'll talk about a very simple compensation scheme, which is what we call gain compensation. Okay, so this is something I remember when one of my professors used to teach. And this was we had the first lecture halls in Pitts Pilani, which is my undergraduate institute. And oftentimes we used to receive feedback signals. Suddenly we would receive a huge ringing noise. So from these audio microphones, which would go through amplifiers. So my analog professor would just say that, the first trick that he would do is just reduce the loop gain, reduce the gain of this amplifier. And suddenly, once he reduces the gain, you'd stop hearing this ringing noise. So reducing the gain is one quick way of fixing this problem. The whole problem arose because the beta became 10. The DC gain increased by a factor of 10. The DC loop gain increased by a factor of 10. So that's why the amplifier became unstable. The circuit became unstable. So now the question is, can we reduce this loop gain somehow? Okay, without affecting this logarithmic operation. So to do that, what we can do here is that we can just add a resistor before this amplifier. So now remember, you need the logarithmic amplification. So I need to reduce the loop gain. So to reduce the loop gain, one way I can do without impacting this, say I need this function minus of Vt ln of Vi upon Is times R. I need this function. So I can't put a resistor anywhere in this path. If I put a resistor here, if I reduce this resistor, then I'm going to affect this transfer function. I don't want to do that. So by adding a resistor here, okay, in the path, I'm creating some kind of voltage division, and we'll see what happens if I've just added a resistor R in this place here. Okay, let's call this resistor Rx. I've called it R here, but let's call this resistor Rx. Okay, so then you have a voltage division from this node. So this is the output of the op amp to this point. So that's going to be, again, I'm going to use a linearized model here. So that's going to be GMR by 1 plus GMR. So you'll have a resistor of value Rx and the looking in impedance into this BJT is 1 over GM. So what you'll have, the loop gain is going to be 1 over GM by 1 over GM plus Rx. Okay, so what you're going to get is 1 by 1 plus GM Rx. So this is the gain from VOP to the output. Multiplied by the loop gain, multiplied by the gain from the output to the inverting terminal. So that will be GM times R. So what I'll get here is an expression that looks something like this. So GM times R is the beta here. That gets multiplied by 1 by 1 plus GM Rx. Okay. So by adding this resistor, I'm introducing a potential voltage division in this path. Okay. I'm tapping this output at the emitter terminal. So the reason I'm doing this is the logarithmic function should not be disturbed. Okay, everything remains the same. It's just like adding a finite output impedance at the op amp. Okay, so what I'm going to get is a loop gain that looks like this: GMR by 1 plus GMRX. For instance, let me choose Rx to be equal to R. In this example, I can do that. I'm going to choose Rx to be equal to R. I can choose Rx to be very different. I can choose Rx to be much greater than R. Okay. Now let's say I choose Rx to be 10 times R, which means GMRx is much greater than 1. So if you recall, GMR was always 10. It was always greater than 10. Okay. So your GMR was 10 for the case when Vi is 250. When it is 1 volt, it is 40. So it's always greater than 10. So if I choose Rx to be much greater than R, then GMRx will be much greater than 1. So this result will be approximately equal to R by Rx. Now if you see, this beta is R by Rx. Okay, it is a factor which is independent of GM. So GM was the variable parameter in the circuit. Okay, because your current was increasing. Vi by R is the current. In one cycle, the current was lower. The other cycle, the current was much higher. It was 4 times higher, and therefore GM was increasing. So that's what was causing this increased loop gain. Okay, change in the loop gain. Now I have eliminated that. Okay, so I've gotten a ratio which is R by Rx. That is your new beta. If I choose Rx equal to R, I'd get beta approximate equal to 1. Okay, so I've taken two values here. So for instance, I've assumed the exact calculation. So let's assume the case where Rx is exactly equal to R. So then what you'll get is GMR by 1 plus GMR. So I have two cases here. In the first case, when GMR equals 10, I'm going to get the ratio beta as 10 by 11. In the second case, when beta, which is equal to GM times R, is 40, I'm going to get 40 by 41, which is going to be 0.98. So now if you see, the loop gain variation was previously a factor of 4. Okay, and of course it is the loop gain itself increased by a factor of 10 once we introduced negative feedback. On top of that, the loop gain variation was a factor of 4 times. Okay, that's like 300% variation. Now the loop gain varies by a factor of less than 7%. Okay, 98 to 0.91 to 0.98. So it is almost less than 7% loop gain variation. On top of that, since beta was 10, it was creating a problem for us. Now beta is just 1. It's close to 1. It's 0.91 or 0.98. Okay, so beta, it's close to 1. So your loop gain remains more or less the same. So if you recall the loop response, the open loop response was looking something like this. You had one pole, and the second pole was coming much later after the UGB. Now this gets multiplied by 0.91 or 0.98. So beta is 0.91 in the first case and 0.98 in the second case. So more or less, the phase margin will remain the same. So you will have a slight variation in this loop gain. So since I'm going to multiply it by 0.91, and in the second case I'm going to multiply it by this is 0.98 and 0.91. So you'll have a slight variation in the UGB and even phase margin. Okay, interface margin will get only better because your loop gain is slightly reduced. So that's one way that I can resolve this problem. So now after I do this fix, after I add this resistor in feedback, the response is going to look something like this. So I had the step response for this step from 250 millivolts to 1 volt. The step response is going to look like a second order. It's going to look like a first order settling. And similarly, I can expect a near symmetric waveform on the other for the negative step as well. So this is a positive step, this is a negative step. The step response will look nearly identical. So remember, I've made a lot of approximations here. So this is a nonlinear amplifier. So I may not be able to do a direct analysis this way, but it works. I mean, it's a reasonably good approximation. And so I've used linear approximations, okay, and tried to estimate the behavior of this circuit, okay. So I could make the waveform nearly symmetric, and also I could stabilize this amplifier. So I can choose the values of Rx to be much greater than R and further stabilize it at the expense of UGB. I can further decrease the UGB. So beta will be, let's assume Rx is 10 times R. So beta will then become 1 by 10. If beta becomes 1 by 10, then your graph will shift lower. Okay, so your graph will shift and you will take a hit on the UGB further. UGB will decrease, okay, but it will be much more stable. Okay, so your response will look like a second order because your time constant has increased, UGB has decreased. Okay, it's going to look much more symmetric and also much more stable. But this works. I mean, making beta close to 1, it's only 7% variation. And since phase margin is 90 degrees, we are still, it will look like a first order response. So that's it. So that's this interesting circuit. Hope you found it useful. I'll soon update some stuff about the PLL lectures. Okay, thank you.